is Anshul Joon, roll number 71, BSc Chemistry Honours, final year. Today we will read Chapter 2, Quantum Mechanics of Pradeep Publication, Volume 3. 2.1 Introduction. The formation of covalent bond was explained for the first time by G.N. Lewis in 1916. He suggested that a covalent bond between two atoms was formed by sharing of electron between the atoms so as to complete their octet and acquire stable configuration. Further, when the atoms approach each other, there are new forces of interaction, that is attraction and repulsion, between the electrons and the nuclei. The forces of attraction being greater than the force of repulsion result into lowering of energy. The internuclear distance at which the system has minimum energy, the stability is maximum. This distance is called the bond length. Lewis' concept could explain the stability of the molecule, and that too only qualitatively. It could not answer some of the questions as follow. First, why do atoms combine to form molecules in some cases but not in others? Example, H2 is stable but not He2. Why only certain combinations are possible but not others? The example, HNO combines to form H2O but H2O2 but not H2O3. Third, why different bonds have different bond energies? Fourth, why molecules have different shape? Example, CO2 is linear while SO2 is bent molecule. The answer to the above questions have been provided quantitatively by quantum mechanics by applying Schrödinger wave equation to calculate the properties of the system consisting of nuclei and electron. The following two different approaches have been put forward. First is valence bond theory, second is molecular orbital theory. The simplest system to be studied was hydrogen molecule ion H2 positive, as it consisted of only two protons and one electron. However, even for such a simple species consisting of three interacting particles, no exact solution of Schrödinger wave equation is possible in classical mechanics as well as in quantum mechanics. Through exact solutions are obtained for hydrogen atom and hydrogen like particle like He positive etc., containing only one nucleus and one electron. Hence, in applying Schrödinger wave equation to even simple molecule or ion, certain approximations are made. One of the most important is Born-Oppenheimer approximation, as explained in the next section. 2.2 Born-Oppenheimer approximation. According to this approximation, it is supposed that the nuclei, being thousands of times heavier than an electron, move relatively very slow and may be treated as stationary, while electrons move with much higher speed relative to the nuclei. For example, calculations suggest that nuclei in H2 vibrate through only about 1 pm, whereas electrons move with the speed of 100 pm, so that the error assuming that the nuclei are stationary is negligible. Taking the example of H2 positive ion, if the nuclei of the two atoms be presented as HA and HB, then in view of the Born-Oppenheimer approximation, the distance between the nuclei may be fixed at an arbitrary value r, and Schrödinger wave equation may be solved for the wave function of the electron, which is a distance Ra from the nucleus HA and distance Rb from the nucleus HB. Thus, in this calculation, R is held constant and only Ra and Rb are varied. Now a new value of R is chosen and the calculation repeated, and so on. This internuclear distance R is a constant parameter in one calculation. When the calculations have been done for a number of values of R, the energy E R of the system may be plotted against R. The curve obtained for H2 positive is shown in the figure 2.2. It is called potential energy curve because the kinetic energy of the nuclei is zero, as they are stationary. From the curve thus behind, from theoretical calculation, the equilibrium bond length Re and bond dissociation energy dE can be obtained from the minimum of the plot. These can be compared with experimental observed values. For example, for H2 positive ion, The observed values for bond dissociation energy and equilibrium bond distance from spectroscopic studies have been found to be 2.78 in, that is 268 kilojoule mole inverse, and 1.06 Armstrong, that is 106 pm respectively. The calculation of potential energy for H2 positive ion is described in the next section. 2.3 Calculation of energy from wave function. The Schrödinger wave equation in the operator form is H psi is equals to E psi. Multiplying both sides of the equation with psi star and integrating over the whole space, we get integrating minus infinity to plus infinity, psi star h psi d tau is equals to integration minus infinity to plus infinity, psi star e psi d tau. As E is constant, the above equation can be written as minus infinity to plus infinity, psi star h psi d tau is equals to E minus infinity to plus infinity, psi star psi d tau. If psi is a real function, equation 3 can be written as E is equals to minus infinity to plus infinity, psi h psi d tau divided by psi minus infinity to plus infinity, psi square d tau. The Hamiltonian operator h is given by h is equals to h square minus h square divided by 8 pi square m delta square v, where delta square is a Laplacian operator which is a function of coordinates x, y, z of the electron. Thus, to obtain the value of E for the given system, we substitute the value of potential energy of the system and should know the correct value, that is true value of the function, which is the solution of Schrödinger equation. In case of hydrogen atom, there is only one proton and one electron. Hence, its potential energy is minus E square by R. In case of the molecules or ions, potential energy has to be calculated from the different interaction between the electron and the nuclei. Moreover, in case of hydrogen atom, only one Laplacian operator is involved for the only electron present, but for the species containing more than one electron, a Laplacian operator is required for each of the electron. Two simple cases are described below. First, hydrogen molecular ion H2 positive. Although the charged species H2 positive cannot be isolated, it is found to be present in high concentration where electric discharge is passed through the distance tube containing H2 gas. This species consists of two protons and one electron. As shown in figure 2.1, if the two protons are represented by HA and HB and the distance between them is kept fixed at R, Born-Oppenheimer approximation, and for one particular position, the electron is at distance Ra from the proton Ha and the distance Rb from the proton Hb, then potential energy of the system is the sum of different electrostatic potential energies found by applying Coulomb law as under. For electron proton Ha interaction, V1 is equals to minus E square by Ra. For electron proton Hb interaction, V2 is equals to minus E square by Rb. For two protons separated by distance r, V3 is equals to V square by r. Hence, total potential energy of H2 positive for the given arrangement of charges will be V is equals to V1 plus V2 plus V3 is equals to minus E square by Ra minus E square by Rb plus E square by r. Thus, Hamiltonian operator for the system is H is equals to minus H square 8 pi square m delta square minus E square by Ra minus E square by Rb plus E square by r. Subsequently, Schrödinger wave equation for H2 positive is H psi is equals to E psi, that is H minus H square divided by 8 pi square m del square minus E square by Ra minus E square by Rb plus E square by r. Psi is equals to E psi. Second, hydrogen molecule H2. The hydrogen molecule H2 contains two proton and two electron for one particular distance r between the two proton and for one electron position. For one particular distance r between the two protons and for one particular position of the two electrons. Different distances are represented in figure 2.3. The potential energy of the molecule will be V is equals to minus E square divided by R A1 minus E square divided by R A2 minus E square divided by R B1 minus E square divided by R B2 plus E square divided by R12 plus E square divided by R. That is equation 9. The Hamiltonian operator will be H is equals to minus H square divided by 8 pi square m del square plus V, where all are the Lipschitz operator referring to the coordinates of the two electrons. Consequently, the Schrödinger wave equation for the H2 molecule will be H psi is equals to E psi, where psi is the total wave function of the two electron in the molecule. The most important quality that still remain to be found to obtain the value of the total E energy of the system is the correct value, true value of the wave function psi. If we do not know psi, we select by a method known as variation method or Ritz linear combination method as described below. Variation method to obtain the correct wave function. We guess some approximate wave function psi 1 on the basis of our knowledge of possible electron distribution and thus then calculate energy E1 according to the equation E1 is equals to minus infinity to plus infinity psi 1 h psi 1 d divided by psi minus infinity to plus infinity psi 1 square d. Similarly, we try a number of wave functions psi 2, psi 3, etc. by considering different possible electron distribution and calculate the corresponding energies E2, E3, etc. Then, according to variation principle, the following results are observed. First, energy E1, E2, E3, etc. will always be greater than the value of true energy E. Second, the trial wave function which gives the lowest value of energy is closest to the true wave function. Similarly, the lowest value of energy will be closest to the true energy. Ritz linear combination method. This is also based on variation method. According to this method, the trial wave function for the diatomic molecule is taken as a linear combination of two wave functions. Example, in H2, the two wave functions are of 1s orbitals. Thus, in general, if the two wave functions combining linearly are psi 1 and psi 2, then the trial wave function is taken as psi is equals to C1 psi 1 plus C2 psi 2, where C1 and C2 are the coefficient which can be varied. Substituting this value of the wave function in equation 4, the energy is calculated. That is, we have E is equals to integration minus infinity to plus infinity C1 psi 1 plus C2 psi 2 H C1 psi 1 plus C2 psi 2 d dot divided by integrating minus infinity to plus infinity C1 psi 1 plus C2 psi 2 whole square d dot. That is equation 14. Now the coefficients C1 and C2 are varied to find out the wave function psi, corresponding to which the energy comes out to be minimum. The condition for getting the minimum energy with respect to coefficients C1 and C2 is that we carry out partial differentiation of equation 14 with respect to C1 and C2 and put the result equal to 0. That is E by del E by del C1 is equals to 0 and del E by del C2 is equals to 0. Combining different result, we get a quadratic equation in E which contains the coefficients C1 and C2. These can be solved to get the values of E, C1, C2 later discussed in section 2.5.2. Similarly, if we trial wave function psi is a linear combination of a number of wave functions psi 1, psi 2, psi 3, etc. with the coefficients C1, C2, C3, etc. We take the trial wave function as psi is equals to C1 psi 1 plus C2 psi 2 plus C3 psi 3 plus so on. The coefficients are then calculated by variation method to get wave function which is closest to the correct wave function, which will give minimum value of energy. The advantage of this method is that if any wrong function is included in the expression for the trial wave function, the coefficient of that wave function will automatically come out to be 0. As mentioned in the beginning, there are two approaches to explain the nature of the chemical bonding and to predict the properties of molecules such as bond distance, bond dissociation energy, dipole moment, etc. These are valence bond theory and molecular orbital theory (MOT). The two theories mainly differ in fact that whereas according to VBT, the atoms are considered to retain their identity, and the bond is formed as a result of the interaction of only the valence electron of the atoms, that is half filled orbital, overlap to form a covalent bond, whereas fully filled orbital do not participate in bonding. On the other hand, MOT considered the molecule as a collection of nuclei, and the electron of the molecule are distributed in different energy level around the group of nuclei, just as electron of an atom are distributed in different energy level of a single nucleus. Just as energy level of an atom are called atomic orbitals, the energy level of the molecule are called molecular orbitals. Thus, according to MOT, all the atomic orbitals of an atom overlap with the appropriate atomic orbital of the other atom. That is, having a comparable energies and proper orientation, unlike VBT, where only half valence atomic orbital take place. 2.4 Valence bond theory. This was the first quantitative theory based on quantum mechanics that was used to calculate the energy of H2 molecule. It was put forward by Hitler and London in 1927 and was further extended by Slater and Pauling. Before we discuss this theory, some basic quantum mechanic principles involved in this theory are given below. First, total wave function psi of two independent systems of the wave function psi a and psi b is equal to their product. That is, it is given by psi is equals to psi a psi b. The total energy E of the two independent systems with energies EA and EB is equal to their sum. That is, E is equals to EA plus EB. The total Hamiltonian is also equal to sum of their independent system, that is H is equals to HA plus HB. For a many electron system, the total wave function is a linear combination of different wave function involved, that is psi is equals to C1 psi 1 plus C2 psi 2 plus so on, where coefficients C1 and C2 etc. are found by variation methods so that psi is closest to the true wave function corresponding to which the energy of the system is minimum. Fifth, the square of the coefficient of any function gives the contribution of that wave function to a total wave function and is usually called weight of that wave function. For the function psi to be normalized, the following condition must be satisfied. C1 square plus C2 square plus C3 square so on is equals to 1. Now let us apply the valence bond theory to the study of bond formation in hydrogen molecule H2. Application of valence bond theory to the study of H2 molecules. Let us start with two hydrogen atoms separated by a large distance so that there are no forces of interaction between them. The electron associated with them by E1 and E2 respectively, that is 2H atom, may be represented as HAE1 and H2E2. Also suppose the wave function associated with these electron are represented by psi 1 and psi a1 and psi b2 respectively. Hence the total wave function for the two separated hydrogen atom will be given by psi is equals to psi a1 psi b2. Now if the two atoms are brought close together and for each distance between the two atoms, potential energy is calculated according to equation 9. Section 2.3, and then total energy of the system is calculated by substituting the value of psi from equation 6. Above in equation 4, section 2.3, we have E is equals to integration minus infinity to plus infinity psi a1 psi b2 h psi a1 psi b2 d tau divided by integrate minus infinity to plus infinity psi a1 psi b2 whole square d tau. Equation 7. If the value of E is plotted as a function of intermolecular distance, the curve I is obtained as shown in figure 2.4. It may be seen that energy of the system decreases with distance till a minimum is reached. This represents the formation of H2 molecule. The decrease in energy corresponding to the minimum represent the bond energy and the distance represent the bond length. However, this curve has been obtained by using the wave function by represented by equation 6. The bond energy is found to be only 24 kJ mole inverse, which is much lower than actual experimental value of 458 kJ mole inverse. Similarly, the bond distance is found to be 90 pm, which is much different from the actual bond length of H2 molecule. that is 74 pm. This shows that the wave function is used in the above calculation. Psi 1, psi A1, psi B2 is not a good approximation. Hence, some other interaction between the two hydrogen atoms will have to be taken into consideration to arrive at the better wave function. The different possible interactions are described below. First, exchange of electron. In writing the above wave function, it was assumed that electrons are distinguishable, that is, electron E1 belongs to HA and E2 belongs to HB. However, the electrons are actually indistinguishable after the overlap of two atomic orbitals. Electron E1 may be under the influence of nucleus of HB, and also electron E2 may be under the influence of nucleus HA. Thus, the system may exist in two different states as follows. First, HAE1, HBE2. Second, HAE2, HBE1. Equation 8. The wave function corresponding to these two states may be written as psi 1 is equals to psi A1, psi B2, and psi 2 is equals to psi A2 and psi B1. Equation 9. The total wave function of the system will then be a linear combination of the above two wave function, that is, psi BB is equals to C1 psi 1 plus minus C2 psi 2 is equals to C1 psi 1 A psi A1 psi B2 plus minus C2 psi A2 psi B1. Equation 10. For H2 molecules, as both atoms are same, put C1 is equals to C2 is equals to 1. Hence, psi BB is equals to psi 1 psi B2 plus minus psi A2 psi B1. Thus, there are two possible linear combinations of the wave function, corresponding to which the wave function may be represented by psi plus and psi negative. That is, psi plus is equals to psi 1 psi A1 psi B2 plus psi A2 psi B1. Psi negative is equals to psi A1 psi B2 minus psi A2 psi B1. Equation 13. If the energy are calculated as a function of internuclear distance by employing the wave function psi negative, the curve 2 obtained, which shows that energy increasing when the atoms are brought close together, thus it does not lead to bonding and represent a non-bonding state. On the other hand, if energies are calculated as a function of internuclear distance by using the wave function psi positive, curve 3 is obtained. It represents decrease of energy with a minimum of a particular distance, and hence represent a bonding state. It is interesting to note that though equation 8 represents two different states, but charge distribution of the two nuclei is same in both cases. That is, each of them represent a state of covalent bond. That is why wave function psi plus is sometimes called covalent wave function and is may be represented as psi covalent. Using the wave function, minimum is the curve found to be at 303 kilojoule mole inverse and at the internuclear distance of 80 pm. Thus, both the values have come closer to the experimental value. The extra lowering of energy that has been observed due to taking into consideration the exchange of electrons between the two hydrogen atoms is called as exchange energy. Thus, the exchange energy of H2 molecule is equals to 303 minus 24 is equals to 279 kilojoule mole inverse. Second is screening effect of electron. When the atoms come close together, the electron of one atom shield the electron of the other atom from the nucleus. Thus, the electron does not feel full attraction by the nucleus. In other words, if the effective nucleus charge is less than the actual nuclear charge, taking this fact into consideration, the wave function was further improved. Using this wave function, energy versus internuclear distance curve obtained is shown as 4 in equation 2.4. The minimum in this curve lies at 365 kilojoule mole inverse, which is shown a further improvement in the value. Third, ionic structure of H2 molecule. Since the calculated value of 365 kilojoule mole inverse is still quite low as compared to the experimental value of 458 kilojoule mole inverse, further improvement in the wave function is required by taking more interaction into consideration. It was suggested that when the atom came close together, both the electron may lie close to nucleus HA or close to nucleus HB, giving rise to two possible ionic structures as follows. 3 is E1, E2, HA, HB. That means HA negative, HB positive. Fourth is HA, HB, E1, E2. That is HA positive, HB negative. Equation 14. Though the possibility of existence of this state is very little because Coulombic repulsion between the electron will be much larger than the attraction between HA negative and HB positive or HA positive and HB negative. Yet by taking this structure into consideration, wave function could be further improved. The wave function corresponding to the states 3 and 4 may be written as psi 3 is equals to psi A1, psi A2. Psi 4 is equals to psi B1, psi B2. The total wave function due to this ionic structure represented by psi ionic may be obtained by linear combination of psi 3 and psi 4. Thus, psi ionic is equals to psi 3 plus psi 4 is equals to psi A1, psi A2 plus psi B1, psi B2. Now combining the covalent and ionic wave functions, the complete wave functions for the system may be written as psi is equals to psi covalent plus psi ionic is equals to psi A1, psi B2 plus psi A2, psi B1 plus lambda psi A1 plus psi A2 plus psi B1, psi B2. Equation 17, where lambda gives the extent of contribution of the ionic structure toward bonding and is usually called mixing coefficient. Its value for H2 is found to be 0.17. Using the above wave function, the minimum curve shown at 5 is found to be at 388 kJ mole inverse, thus bringing the value still closer to the experimental value of bond energy 458 kJ mole inverse. The bond distance is found to be 75 pm, which agrees fairly well with the experimental value of 74 pm. Further improvement in the wave function has been done, but it will not be discussed here. It is important to mention that valence bond theory led to the concept that a molecule or ion is in between the different structures. The phenomena is called resonance and the different structure are called resonating structure. The actual structure is more stable than any of the resonating structure. Thus the concept of resonance follows the VBT. 2.5 Molecular orbital theory. This theory gives an alternative method to set up an expression for the wave function psi and is used more frequently. The theory was developed by Hahn, Millikan, Haeckel and others. It differs from valence bond theory mainly in fact that according to this theory, the electron in a molecule is not considered to be under the influence of a particular nucleus but is considered to be under the influence of all the nuclei present. The total wave function is the product of the wave function for various electrons involved in the bonding. 2.5.1 Basic ideas of molecular orbital theory. First, a molecule is considered as a group of nuclei. All the electrons are distributed around this group of nuclei in different energy level. Just as in atom, the electrons are distributed in different energy level around a single nucleus. Just as energy level of an atom are called atomic orbitals, the energy level of the molecules are called molecular orbitals. Thus, whereas atomic orbitals are monocentric, the molecular orbitals are polycentric. Second, each electron or each molecular orbital in the molecule is described by a wave function called molecular orbital wave function, the correct value of which can be found by a method called linear combination of atomic orbitals, LCAO method. Second, each molecular orbital is associated with a definite amount of energy, the correct value of which can be calculated from the correct value of the wave function by applying Schrödinger wave equation. Fourth, the significance of molecular orbital wave function is same as that of the atomic orbital wave function. Thus, just as an atom, psi square d tau gives the probability of finding the electron in a volume element, d tau is in a molecule, psi square d tau gives the probability density or electron charge density in the volume element d tau. Fifth, the size, shape and energy of the molecular orbital formed depend upon the size, shape and energy of the atomic orbital combining to form molecular orbitals. The atomic orbitals combining together lose their identity to form new orbitals called molecular orbitals. Sixth, Only these atomic orbitals combine to form molecular orbitals which have comparable energies and same symmetry with respect to the molecular axis so that maximum overlapping is possible. Seventh, the filling of electrons into molecular orbital take place according to the same rule as followed by the atomic orbitals, that is Aufbau principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. 2.5.2 Linear combination of atomic orbitals LCAO, that is H2 positive ion. One of the best ways to construct a molecular orbital wave function, or simply called molecular orbital, is by approximation of linear combination of atomic orbital, or in short called LCAO approximation. To understand this method, let us consider the simplest case of hydrogen molecular ion H2 positive. H2 positive ion consists of two protons HA and HB separated by a distance r and only one electron. The electron is considered to be moving in a molecular orbital under the influence of both the nuclei. When at some instant the electron is in the neighborhood of A, it will behave as if it was moving in the atomic orbital of HA, and the effect of the nuclei HB will be negligible. Similarly, at some other instant, the electron may be in the neighborhood of HB so that the influence of the nucleus of HA and the electron is negligible, and the electron will behave as if it were moving in the atomic orbital H of HB, state 2, shown in figure 2.5. In the first case, the wave function of the electron will be psi A, that is like that of the electron in an atom HA, and in second case the wave function of the electron will be psi B, that is like the electron in the atom HB. In between these two extreme situations, the electron may be present in a position where it may be under the influence of both the nuclei and hence may have characteristic of both the wave function psi A and psi B. The wave function of the system, called molecular orbital wave function psi MO, is then obtained as a linear combination of psi A and psi B according to the expression psi MO is equals to C1 psi A plus C2 psi B, where C1 and C2 are the coefficient of the wave function psi A psi B, such that their square, that is C1 square and C2 square, give their contribution weightage toward the molecular orbital wave function. The potential energy of the system is calculated as already explained in section 2.3, and the total energy of the system is calculated by applying Schrödinger wave equation, which leads to the following results. As already explained in section 2.3, E is equals to integrating minus infinity to plus infinity psi h psi d divided by integration minus infinity to plus infinity psi square d. Substituting the value of psi from equation 1, it gives E is equals to integration minus infinity to plus infinity C1 psi A plus C2 psi B h C1 psi A plus C2 psi B d dot divided by integration minus infinity to plus infinity C1 psi A plus C2 psi B whole square d dot, that is equation 3. The coefficients C1 and C2 are found by variation method, which give minimum value of the energy E. The condition of getting minimum energy with respect to the coefficient C1 and C2 is that what we carry out, that is we put delta E divided by delta C1 is equals to 0 and delta E divided by delta C2 is equals to 0. Combining result of the different equation, we get a quadratic equation E, which also contain the coefficient C1 and C2. The solution of the quadratic equation gives two roots of E. They are represented by E plus and E negative. The symbol E plus indicate molecular orbital with energy lower than that of combining atomic orbitals EA, EP, and E negative is represents the unsubstituted separately in the quadratic equation in the energy obtained above, and we get two equations in terms of C1 and C2. Applying normalization conditions for the molecular orbital wave function, we can calculate the values of C1 and C2 for the two molecular orbitals, one with the energy E positive and the other with E negative, explained below. From the basic principle of quantum mechanics, We know that function psi is acceptable solution of Schrödinger wave equation only if it is normalized, that is, it must satisfy the condition um, psi square mo d tau is equals to 1 integration c1 psi a plus c2 psi b whole square d tau is equals to 1, that is c1 square psi a square d tau plus c2 square integration psi b square d tau plus 2 c1 c2 integration psi 1 psi 2 b d tau is equals to 1. But as the atomic orbital of the wave function psi a and psi b combining to form molecular orbital wave function are normalized, we have psi square a d tau is equals to 1 and integration psi square b d tau is equals to 1. Substituting these values in equation 6 representing the integral between the orbitals psi a and psi b, we get c1 square plus c2 square plus 2 c1 c2 s is equals to 1. The zero overlap approximation, we put s is equals to 0 and hence the normalization conditions become c1 square plus c2 square is equals to 1. Further, in case of H2 positive, both the atoms nuclei are the same, whereas will be equal weightage by the atomic wave function psi a and psi b toward the molecular orbital wave function. Hence we will have c1 square is equals to c2 square. Combining results, we get c1 is equals to plus minus c2 is equals to plus minus 1 by 2. Two sets of values are possible for c1 and c2, that is plus 1 by root 2 plus 1 by root 2 and plus 1 by root 2 minus 1 by root 2. Substituting these values, two linear combination are possible. One by using first step values of c1 and c2 is represented by psi plus mo, and the other by using second set of values represented by psi negative mo. Thus we have psi plus mo is equals to plus 1 by root 2 psi a plus 1 by root 2 psi b is equals to plus 1 by root 2 psi a plus psi b. Psi negative mo is equals to plus 1 by root 2 psi b psi a minus 1 by root 2 psi b is equals to 1 by root 2 psi a minus psi b. The wave function psi positive mo corresponds to the energy E positive, whereas psi minus mo corresponds to the energy E negative. Equation 12 and 13 gives the correct value of the wave function according to LCAO MO treatment of H2 positive ion. Using this wave function, energies E positive and E negative are calculated for different internuclear distance r. A graph is then plotted between energy versus internuclear distance. The potential energy curve thus obtained for H2 positive ion are shown in figure 2.6. The potential energy curve of psi positive MO shows a minimum at 171 kJ mole inverse and internuclear distance of 132 pm. The actual observed values are 268 kJ mole inverse and 106 pm. Thus, the agreement between the calculated value is not very satisfactory. Hence, a number of further improvement have been introduced, but we shall not discuss here at this level. 2.6 Physical picture of bonding and anti-bonding wave functions. We have seen from above LCAO MO treatment of H2 positive that on calculations two values of energies are obtained for this system, represented by E positive and E negative. Their corresponding wave functions represented by psi positive MO and psi negative MO are given by equation 12 and 13 in section 2.5. The value of E positive is found to be lower than the energy combining atomic orbitals, that is EA and EB of thus isolated atoms HA and HB. Thus it leads to a greater stability and hence is responsible for bonding between HA and HB. The molecular orbital formed is called bonding molecular orbital. On the other hand, the value of E negative is found to be higher than that of the combining atomic orbitals. The molecular orbital thus formed has lower stability and hence is called as anti-bonding molecular orbital ABMO. Further, it is found that the extent of lowering of energy is almost equal to the extent of increase in energy. Hence, a physical picture of the bonding and anti-bonding molecule orbital formed from atomic orbitals may be represented as shown in figure 2.7. Another important result that follows from the expression for the wave function equation 12 and 13 in section 2.5 may be obtained as follows. Rewriting expression for the wave function psi plus and psi negative, we have psi positive mu is equals to 1 by 2 root 2 psi a plus psi b. Psi negative mu is equals to 1 by root 2 psi a minus psi b. That is equation 1 and 2. Squaring both sides of this equation, we get psi plus square is equals to 1 by 2 psi square a psi square b plus 2 psi a psi b. Equation 3. Psi negative square is equals to 1 by 2 psi a square psi b square minus psi 2 psi a b. Equation 4. As psi square gives the probability of finding the electron, and psi plus square is greater than 1 by 2 psi square a psi square b, because there is an extra positive term in equation 3, and psi 2 negative is less than 1 by 2 psi a square plus psi b square, because there is a negative term in equation 4. This shows that the probability of finding electron in the region between the nuclei increases the case of bonding molecular orbital, whereas this decreases in the case of anti-bonding molecular orbitals. As compared to their probabilities in the separated atoms, the presence of the greater electron density between the nuclei results in the greater attraction by both the nuclei, hence decreases in energy. Further, it is important to point out here that in equation 2.7, the anti-bonding molecular orbital has been raised by the same energy by which the bonding molecular orbital have been lowered. However, if more precise calculations are carried out, the ABMO is raised slightly in more energy than energy which BMO is lowered, though the general pattern of the diagram remain the same. For example, if overlap integral S were not neglected, equation 8 section 2.5.2, the wave function psi positive and psi negative will be given by psi positive is equals to 1 by under root 2 plus 2s psi a plus psi b, and psi negative is given by 1 by root 2 minus 2s psi a minus psi b. Equation 5 instead of equation 1 and 2. To sum up, the main point about the bonding and anti-bonding molecular orbitals are given below. First, whenever two atomic orbitals psi a and psi b combine together, their linear combination gives rise to two new molecular orbitals psi plus and psi negative. The energy E positive corresponding to the molecular orbital psi positive is lower than that of the combining atomic orbitals. Hence, it has the greater stability than the combining atomic orbitals and is therefore called as bonding molecular orbital. Third, the energy E negative corresponding to the molecular orbital psi negative is greater than that of the combining atomic orbitals. Hence, it is less stable than the combining atomic orbitals and is therefore called the anti-bonding molecular orbital. Fourth, the amount of lowering in energy of the BMO is almost equal to the increase in energy of the ABMO with respect to the combining atomic orbitals. However, more precise calculation reveal that the increase is slightly more than decrease. Fifth, the electron belonging to an atomic orbitals no longer remain in the atomic orbital but enter into the bonding and anti-bonding molecular orbital in order of their increasing energies. The molecular orbital with lower energy being filled first according to the Aufbau principle. Thus, if two H atoms combine to form H2, the electron originally present in one S atomic orbitals now enter into the bonding molecular orbitals. Sixth, on the basis of LCAO calculation, it is found that greater is the extent of overlap between the combining atomic orbitals, greater is the lowering energy of BMO. Main points of difference between the BMO and AMO are summed up in table 2.1. 2.7 Variation of electron probability density along internuclear axis in bonding and anti-bonding molecular orbitals. 1 by graphical representation. A. Bonding molecular orbitals. As already explained in section 2.5, equation 12 and 13, the bonding molecular orbital wave function of the two atomic orbitals, wave function psi a and psi b, is given by psi positive is equals to 1 by root 2 psi a plus psi b. Hence, the electron probability density in the bonding molecular orbital will be psi plus square is equals to 1 by 2 psi a plus psi b whole square is equals to 1 by 2 psi square a plus 1 by 2 psi square b plus psi a plus psi b. The sum 1 by 2 psi square A plus 1 by 2 psi square B gives the electron probability density between the nuclei of the two atoms in the uncombined state. Note that it is not also equal to psi square A plus psi square B. However, psi square A and psi square B gives the electron probability density of the electron in separate atom A and B respectively. Plotting the value of square plus along the internuclear axis, also plotting the value of psi square A and psi square B for the individual atom A and B. The curve obtained are shown in figure 2.8. For psi plus square, the curve has been shown by solid line. For psi square A and psi square B, these lines have been shown by dotted lines. It may be seen from the plot that there is a greater electron probability density between the nuclei in BMO than in the uncombined atomic orbitals. B. Anti-bonding molecular orbitals. For the anti-bonding molecular orbitals, the wave function is psi negative is equals to 1 by under root 2 psi A minus psi B. Hence, the electron probability density will be given by psi negative square is equals to 1 by 2 psi A square plus 1 by 2 psi square B minus psi A psi B. Plotting the values as before, the curve obtained are shown in figure 2.9. From the plot, it may be seen that the electron probability density in the middle of the nuclei corresponding to the distance r by 2 in the AVMO is almost zero. This means that the electron tend to stay away from this region, hence there is greater repulsion between the nuclei. Thus, there is a plane passing through the point exactly in the center between the two nuclei and the perpendicular to the internuclear axis, on which the electron probability density is in AVMO is zero. This plane is called the nodal plane. Second, by three-dimensional contour diagram. According to this method, the electron probability densities are calculated at different points around both nuclei. Points shown in the same probability density are joined together. The resulting surface obtained is called a contour. A number of contours thus obtained around both the nuclei for bonding and anti-bonding molecular orbitals. These are shown in figure 2.10 below. 2.8 Criteria for forming molecular orbitals from atomic orbitals. It has already been explained in the preceding section that molecular orbitals are found by linear combination of atomic orbitals. However, it is important to note that any two atomic orbitals cannot combine to form molecular orbitals. They combine to form molecular orbitals only if the following conditions are satisfied. First, the combining atomic orbitals must have comparable energies. Thus, in the formation of a homonuclear diatomic molecule A2 like H2, O2, etc., first AS orbitals of one atom can combine with 1s of the other, 2s of one atom and 2s of the other, and so on. But 1s of one atom cannot combine with 2s of other because they have a large difference of energy. However, such a combination may be possible in the case of heteronuclear diatomic molecule AB. This is on account of the fact that combining atomic orbitals psi A and psi B have comparable energies in their coefficient. Ca and Cb have comparable values. As a matter of fact, if the two combining atom identical, they will have the same coefficient, that is Ca is equals to Cb. The combining atomic orbitals must overlap into a considerable extent. This is because greater is the extent of overlap, greater is the electron density in the internuclear region, and hence greater is the attraction of the electron density by both the nuclei and less in the repulsion between the nuclei. The combining atomic orbitals must have same symmetry with respect to the molecular axis. The example taken in the z-axis as the internuclear axis, as an s orbital can overlap pz orbital, or pz orbital can overlap with pz orbital, but z orbital cannot overlap with py or px orbital. Similarly, px can overlap with px, or py can overlap with py, px, but cannot overlap with pi. In the SPX, a small overlapping has been shown in our figure using proper sine wave function. Area of positive overlap is equals to area of positive negative overlap. Thus, two areas are equal but opposite in sign. Hence, positive overlap is cancelled by positive negative overlap, and the sum is 0. Comparison of VBT and MOT methods. Point of similarities. First, both the models make use of atomic orbitals wave functions psi A and psi B of the electron involved. Second, according to both the models, the bond is formed due to greater electron charge density in the internuclear region. Third, both the models postulate that found bond is formed between the atoms due to overlap of their atomic orbitals. Fourth, according to both the models, the combining atomic orbital must have comparable energy and same symmetry with respect to the internuclear axis. Both the methods represent approximation. Point of difference. First, according to VBT, only the valence electron take part in the bonding and hence atoms do not lose their identity even after overlap. Whereas according to MOT, all the electron distributed around all the nuclei taken together, hence atom loses their identity. The energy level in which the electron of the molecule are distributed are called molecular orbitals. Second, according to VBT, the only half-filled orbital of the valence shell take part in the bonding, whereas according to MOD, all the orbitals that is half-filled as well as fully filled combined together provided they have comparable energy and same energies. Third, according to VBT, the total wave function obtained as a linear combination of the two wave functions psi 1 is equal to psi a1 psi b2 and psi 2 is equal to psi a2 psi b1 is given by psi vb is equal to psi a1 psi b2 plus psi a2 psi b1. Equation 12 section 4, 2.41. According to MOT, the total molecular orbital wave function is given by equation psi mo is equal to psi a1 plus psi b1 into psi a2 plus psi b2. Equation 3 section 2.102. On multiplying, this equation becomes psi a1 psi b2 plus psi a2 psi b1 plus psi a1 psi a2 plus psi b1 psi b2. In this equation, the first two terms are same as those of the psi vb in equation 1, hence equation 3 becomes psi mo is equals to psi vb plus psi a1 psi a2 plus psi b1 psi v2. The last two terms correspond to the ionic structure, that is when both the electrons are on A or both the electrons are on B, H negative A, H positive B and HA positive, HB negative respectively. Thus, MO to justify the contribution of the ionic structure, whereas in BBT, these terms were included later but were just present in the original VBT. Fourth, the VBT lead to the concept of resonance, whereas MOT has nothing to do with resonance. MOT explained paramagnetic behavior of the number of molecular and their ions, while VBT fails to do so. Sixth, molecular orbital method is less complex mathematically than valence bond method, hence is applied. Note, as discussed earlier in this chapter, the energy calculated using psi VB is better agreement with experimental values than calculated using psi MO. Hence, we may conclude that the contribution by the ionic structure should not be included in the wave function with equal weightage. Their contribution is taken as only 0.17 H2 molecule. However, in other molecule, particularly when the atom involved are different, the ionic form may take significant contribution and their inclusion may give better result. Thus, neither of the two methods may be considered as better than the other. Depending upon the situation, that is the nature of the molecule being studied, either of the method may be given better result. Thank you so much.